Hey y'all, my name is Prashant Kumar, or PK, and I'm an MCAT tutor at Shemmassian Academic Consulting. Today, we're going to be doing a passage walkthrough in the MCAT Chem Phys section. You should be taking roughly 6.5 minutes on this passage, but today we're going to be going more in depth so you can see exactly what's going on in my head as I tackle this section. Let's get it. Alright, so I've gone ahead and put the passage on the left and the questions we're going through on the right. So feel free to take a moment, pause the video, and come back to us. I'll go ahead and zoom in on the passage so you can take a better look at it. So here's the passage, and then here are the questions. Great, so feel free to pause, take as much time as you need, and we'll get right into talking strategy. For me, I like to maintain the same strategy regardless of whatever passage I'm going through. The reason for this is it gives me something to come back to regardless of whether the passage is super easy or super hard. It gives me a routine in a sense. So for me, that builds my confidence, and on test day, confidence is super important and helps you save as much time as possible. I know exactly what I'm going to do when I come into test day. That strategy looks like read a paragraph, write a 3 to 5 word summary, go on to the next paragraph, do the same, and on and on and on. For me, this gives me a little check-in at the end of each paragraph, making sure I understand exactly what's going on before I move on to the next one. Kind of a mental accountability for understanding. So after that, I don't waste time having to reread an entire passage. Oftentimes I'd find myself getting lost in the passage and having to come back if I didn't understand anything and reread the entire passage. With this, if I don't understand a paragraph, I can just reread the paragraph at hand. And that saves me a lot of time in the long run. And the third thing is, when I have figures, I don't spend too much time on the figures on that first read. The reason for this is, if a question asks me to come back to the figure, I'm going to inevitably have to come back and look at the figure. I don't want to waste too much time, especially when time is such a hot commodity on the test. And so with that, let's get right into the first paragraph. Fluorine-18 radiolabeling typically includes several conserved steps, which includes elution of 18 fluorine from an anion exchange cartridge with a basic solution, K2CO3 or KHCO3, in cryptofix 2.2.2, in a mixture of acetonitrile and water, followed by rigorous azeotropic drying to remove the water. Researchers attempted to develop a non-anhydrous and minimally basic NAMB technique to simplify the process and avoid basic conditions that can limit the scope and efficiency of 18F fluoride incorporation chemistry. All right, so what's happening is the question I always ask myself. I check in, do I understand anything? And I want you to think big picture understanding. I don't really care if you know every detail, every word, just a big picture understanding of what exactly is going on and why we're talking about this paragraph. So for me, that's looking at we're gonna look at fluorine-18 radio label method, okay? So remember, there's so many words that I don't know or I'm not familiar with, and that's fine. Like, who knows what azeotropic means, but I don't off the top of my head. And so with that, we can start with that paragraph, just to understand that this is where it talks about like all of these methods and come back to it if we need to. It's kind of a table of contents for the passage. In a novel approach, researchers eluted 18 fluorine from small 10 to 12 milligram anion exchange cartridges with solutions of tetraethylammonium bicarbonate, perchlorate, or tosylate in polar aprotic solvents containing 10 to 50% water. After dilution with additional aprotic solvent, these solutions were used directly in nucleophilic aromatic and aliphatic 18F fluorination reactions, which prevents the need for azeotropic drying. Okay, so what is happening? What's being talked about? So this is the novel approach with aprotic, right? So that's what it's talking about. It's talking about this aprotic solvent that's used in this sort of new method. So we talked about the traditional radiolabeled method in the first paragraph, and then this new approach with this aprotic solvent. Awesome. As proof of principle, MAB chemistry was utilized for the synthesis of the dopamine D2-D3 antagonist, 18F phallipride. The standard synthesis of 18F phallipride is known to be base sensitive because of the tendency of the tosyl phallipride precursor 6 to undergo hydrolysis and elimination side reaction, making this a compound a good candidate with which to evaluate this minimally basic synthesis. All right, and then we have a figure 1, NAMB chemistry synthesis of 18F phthalate. All right, so what is happening? What's the question? So here we're looking at 18F phthalate. And so why are we looking at that? Because it's a check of synthesis, right? Of synthesis. And so here it's literally saying we're evaluating this minimally basic synthesis with this candidate, right? And so that's why I want to make sure that we understand every single one of these. We're trying to create this 18F phthalate to check if our experimental novel approach is working. And so with that, we have a fully functional understanding of everything in the passage, and we're good to go right into the questions. And remember, I'm not going to take a look at the figures too much in depth. All I see is some sort of reaction into this 18F phthalate. And so with that, we can get right into question number 1. All right, question number 1. In a novel experiment, researchers find a new 18F fluoride that can carry out NAMB chemistry upon electron capture. Which of the following best describes the element after positron emission? Is it A, 18F fluoride, B, 17F fluoride, C, 18O oxygen, or D, 17Ne neon? All right, so right away we should understand that this is a standalone question. It's not asking us to go back into the passage anywhere. It's asking us a pretty direct question. Basically, what is the element after positron emission? And so this is a type of sort of radioactive nuclear reactions where we are emitting a positron. And what does that mean? That means we are emitting a proton and changing it to a neutron, right? So this is a type of beta decay where we have a beta molecule, but in this case it's a positron, not an electron. So there's beta minus decay and beta positive decay. So beta minus decay is when we emit an electron, and beta plus decay is when our proton turns into a neutron. Neutral. Okay, I'll draw a neutral. Okay, perfect. And so here in this positron emission, right, we start with fluorine, which is 18. And I always write out the protons as well. So we have fluorine 18,9, makes sense. And then we're emitting a positron. And so what does that mean? Well, we have our beta molecule with a +1 and a 0, right? And so what does that mean? Well, now we're looking at this. We're looking for this molecule that we don't know. And so what we have to do is make sure that the top adds up together and the bottom adds up together for the left and the right side. So for the top, we need to make sure that this 18 matches this plus whatever's up here in our mystery chemical compound. So I'll just write X for now. So if we wanted the left side to match the right side, then the top has to be 18 as well, right? 18 plus 0 is equal to 0, or it's equal to 18, right? 18 is equal to 0 plus 18. Perfect. Now we need to make sure the bottom side makes sense. So here we have 9 again, right? So 9. And so we need that to add up to whatever this is. So something 1 plus something else. And so we should be able to say, okay, 1 plus 8 equals 9, right? The left side is 9, the right side is 1 plus 8, 9 equals 9. And so here we have 18 on top, 8 on the bottom. And so which one of the chemical atoms will this match? And that would be C, right? Oxygen is the one with 8 protons, and it has a mass number of 18, so it matches exactly what we're looking for. Right away, if we notice the top, we could even eliminate B and D right away because they don't have 18 at the as the mass number. But right away, we can say C is our answer and eliminate A because of the protons. Awesome. With that, we're going straight into question number 2. Researchers discover that high concentrations of a protic solvent in a new experiment prevent nucleophilic aromatic 18F fluorination reactions necessary for product formation. Which of the following best explains this observation? Is it A, protic solvents will hydrogen bond with nucleophiles, thereby decreasing nucleophilicity? B, protic solvents will hydrogen bond with electrophiles, thereby decreasing electrophilicity. C, protic solvents will form van der Waals interactions with aromatic rings, thereby decreasing nucleophilicity. Or D, protic solvent will form dipole-dipole interactions with electrophiles, thereby decreasing electrophilicity. All right, so this is another sort of standalone question, right? Where we're talking about, we have a protic solvent and it's preventing nucleophilic aromatic fluorination. But we're asking, why is this occurring, right? What explains this observation? And so to do this, we need to understand exactly what a protic solvent is. And the way I like to think of it is it's a solvent where we have this sort of the most FON, the most electronegative atoms attached to H's, right? It can be any of these three. And so when we're in the solution, right, if we have a bunch of OH's, that gives context for a certain type of bond, specifically a hydrogen bond, right? If you have FON, or the most electronegative atoms attached to a hydrogen, this gives way for hydrogen bonding. So right away, when we see protic solvent, we can think hydrogen bond, and there's only two answer choices left that talk about hydrogen bonds. It's A or B. Van der Waals interactions, not really specific, always exist, so it's not even gonna be relevant. And aromatic rings also doesn't make sense. Dipole-dipole interactions, they exist, but they're nowhere near as important as hydrogen bonds when we're dealing with the most electronegative atoms. And so now we're debating whether the hydrogen bonds will interact with the nucleophiles or the electrophiles. So that's the next question, right? If it interacts with the nucleophiles, then obviously it'll decrease nucleophilicity. If it interacts with the electrophiles, it'll decrease electrophilicity. So now we need to ask ourselves, is it dealing with the nucleophiles or the electrophiles, right? And so right away, we should think that this will deal with whatever is more likely to interact with the electronegative molecules. And that would be anything that is nucleophilic. The reason for this is I want you to think of anything that traditionally is nucleophilic, right? So if we just had a free oxygen or an OH group on the end of a molecule, right? Or an O on the end, right? If we wanted to attack something else, it would be very, very easy to, because that's very nucleophilic. But once we start adding these F's, these N's, these O's with the H's on it, we create these hydrogen bonds between them, right? And so when we have these hydrogen bonds, then it becomes more stable and it's less likely to attack something. So I want you to think of the nucleophile as the attacker and sort of the protic solvent as something that's kind of stabilizing it so it doesn't want to attack anymore. And so in this case, if we have this O negative charge or an N minus or whatever, right? It's going to be stabilized by the hydrogen bonds. Whereas if we looked at the electrophiles, right? What's an example of a common electrophile? Sort of any sort of like an aldehyde or anything like that, right? You're not going to have, if we draw, right? Something like that. And we have this in the same solution. It's not going to interact in the same way, right? It's not going to be able to hydrogen bond in the same way that a nucleophile is being stabilized. And so in this case, the electrophilicity would not change, but the nucleophilicity would. And so we can eliminate B and we're left with A. Awesome. Question number 3. Awesome. Which of the following functional groups present in compound 6 is important for the hydrolysis side reaction? Is it A, ether, B, ester, C, amide, D, amine? All right, so first we have to look at compound 6, right? And we don't know where it is, but we're looking for somewhere where a hydrolysis side reaction would occur. So compound 6, where is it? It's right here. It's compound 6, tosylphalopride. And so we're looking for a functional group that is existing and probably going to be at the site of an electrophile, or where something will be attacked. And so right away, I want you to pay attention to this one, right? This is a very common sort of structure called an amide. We see this very, very frequently, right? An amide, very, very electrophilic. We see this with peptide bond hydrolysis. When we have the amino acids linked together and a water molecule comes and attacks, then the peptide bond breaks. And so right away, we see something that's looking very, very strong. And so I'm going to mark amide as a great answer. Now, let's look at amine, right? An amine is just an N attached to H, R groups, right? There's primary, secondary, tertiary amines. These are never going to be electrophilic. They're never going to be attacked very, very commonly. And so we can eliminate D. Ester and ether. What are these? An ester is a double bond O attached to an O followed by an R group, right? And an ether is sort of an O attached to an R and an R group on both sides. And so an ether is definitely not going to be electrophilic. You're never going to see something attack an ether because there's two R groups on both sides that are stabilizing it. An ester is slightly more electrophilic. It is the common site of attack, but it's nowhere near as electrophilic as an amide, right? Because it's stabilized by this R group, and amide has the N attached to an O, very, very commonly broken, and so we're going to eliminate B, and we're choosing C. And so something very, very important is I want you to go through the functional groups in your own time and see which ones are electrophilic and which ones are nucleophilic, right? This is a very, very important understanding that you'll see over and over again on test day. So if you have a basic understanding of which ones are the most electrophilic and which ones are the most nucleophilic, these are trends that can help you identify molecules and honestly solve questions like this, right? You're able to identify which one's slightly more electrophilic, and as a result, which one's going to be undergoing a hydrolysis side reaction. And so with that, we are 3 for 3 and on to the last question. Question number 4. Okay. Researchers are having trouble obtaining pure compound 6. They hypothesize that protonating the amide nitrogen in compound 6 will allow them to use which of the following columns for purification? Is it A, anion exchange because the positive charge on 6 will bind the negatively charged resin? B, anion exchange because the negative charge on 6 will bind the positively charged resin? C, cation exchange because the positive charge on 6 will bind the negatively charged resin? Or D, cation exchange because the negative charge on 6 will bind the positively charged resin? Okay, so this is a sort of a branch question where we're looking on whether it's anion or cation exchange, as well as whether there's a positive or a negative charge, with the opposite being this. Okay, and so this is kind of like a 2x2 question where you'll have two parts, and if we identify one part, we can eliminate two of the answer choices. Okay, so researchers are having trouble identifying pure compound 6, and they want to protonate an amide nitrogen, right? And so if you protonate an amide nitrogen, what will you have? You will have a positive charge on the amide, right? You'll have a positive charge. And so when we run through an anion exchange, right, we're going to have this sort of column. And so I'm going to give you a brief summary of how this works, and then I want you to identify what will happen in this case, right? So the idea is when we have anion exchange, anion is traditionally a negatively charged ion, and a cation is traditionally a positively charged ion. Okay? So if we're exchanging anions, right, we're going to be exchanging the ions with a negative charge, right? So anion means we're exchanging negative, cation means we're exchanging positive. And so with that understanding, we're actually able to do a lot, right? So in this case, we have a positive charge, so which one's going to be exchanged? The cation. And if we think of that, the A and B are automatically eliminated, which is the great part of 2x2 questions. So the idea is that this positive charge will be exchanged. And so with that, we're able to say C is actually a better answer than D because the negative charge is not being changed in a cation. The positive charge is being changed in a cation. And the way this experiment works is that we have this resin on the side that is negatively charged in this case, right? Negatively charged along the sides. And so when we run this compound 6 through it, the positive charge, I'll draw it in green, will be attracted to these negative charges, okay? Then this is a big picture understanding. If you want more information, just Google it or look at the Shemmassian website. And so the positive charge will line the walls because they're being attracted by the negative. And so there will be cation exchange. The positive ions will be exchanged because they bind to this negatively charged resin. And with that, we have a basic understanding of what's happening as we elute compound 6 through this column. And we are 4 for 4, we crushed it. All right, great work, team. We crushed another Chem Phys passage. Kudos for you for getting it done. Some great topics from experimental design and cation and anion exchange to how functional groups work and all of that. So great job getting it done, and hopefully that bridged some gaps in the content for you. If you like this video, give us a like down below and subscribe to our channel, and comment exactly what types of videos you're looking forward to next and content you want from the YouTube channel. Additionally, check out our 528 strategy series from Vikram. Super helpful strategies for each of the sections so you can get your dream score on test day. And finally, click the link in our bio to sign up for the MCAT question of the day so you don't miss out on any test prep before test day. Happy studying, and let's get it.